Let's look at some problems where we're verifying identities. In some of these, we're just going to do parts of that. In number 9, all we're wanting to do here is put this expression in terms of sine and cosine and then simplify as much as we can. For these, you're going to use the reciprocal identities and the quotient identities. Tangent is sine over cosine. That means that tangent squared would be sine squared over cosine squared. There we used a quotient identity. Cotangent, remember we're wanting to write these in terms of sine and cosine, so another quotient identity is that cotangent is cosine over sine. For both of these two, we'll use our reciprocal identities. Secant is 1 over cosine, and cosecant is 1 over sine. Now we have everything in terms of sine and cosine. Now we just want to simplify this, so we're going to cancel anything that matches between the top and the bottom. So we can cancel a cosine here and here. And here we've got sine of theta times sine of theta. That's sine of theta squared, so we can cancel that with the sine theta squared that's up here. Now all we have left is a 1 on the top, and we have a cosine squared on the bottom. We can use one of our reciprocal identities again. 1 over cosine is secant, so this would be the same as secant squared theta. And that's as simple as we could possibly get this. In this one, we're just trying to perform the operations that are there and then simplify as much as possible. Since we've got two rational expressions, probably what we would want to do with this is get a common denominator and then put the two rational expressions together. In this expression, we've got cosine for a denominator. In this one, we've got sine times cosine. That means our least common denominator would be sine theta times cosine theta. That means we just need to rewrite this first expression, since this one already has the LCD that we want. So to give this a denominator of sine theta times cosine theta, that means we're multiplying both the top and the bottom by sine of theta. And then this one we're not going to change. Now on the top of this one, sine theta times sine theta would give us sine squared theta. Now that our denominators are the same, we can go ahead and subtract our two numerators. That's going to give us sine squared theta minus 1 on the top, and that's all over sine theta times cosine theta. Now we want to keep simplifying this as much as possible. And anytime you see one of our functions squared together with a 1, you should think about either the Pythagorean identities or some of our other identities. This one happens to be the reverse of one of the forms of our Pythagorean identities, and that is sine squared theta plus cosine squared theta equals 1. If we subtracted sine squared theta from both sides, we'd have 1 minus sine squared theta. This is the reverse of that with both of the signs changed. So that means that this would actually be the opposite of cosine squared theta. Now that we've done that, we've got a cosine squared on the top and a cosine on the bottom, so we can cancel one of those cosines. That gives us just cosine theta on the top, sine theta on the bottom, with the negative out front. Cosine over sine is the same as cotangent, so the simplest we could write this would be negative cotangent of theta. In number 11, we're actually trying to verify the identity. One of our strategies for verifying identities was to look at the most complicated side first and just work with that one side. In this one, I'd say that this side is more complicated, so let's just work with that side. One thing we could do, since we've got two terms here and they both have a cosine theta, is we could factor out the cosine of theta from both of these terms. That would give us a 1 here and a minus sine squared theta here. Now we can use one of the alternate forms of our Pythagorean identity. 1 minus sine squared is the same as cosine squared. So this is using this identity in a different form. If we just subtract sine squared from both sides, this is the same as cosine squared. Now we can go ahead and multiply these two together. We have cosine times cosine squared. When we multiply those two together, we get cosine cubed, and that's what we were trying to get to. Now we're going to work with our inverse trig functions. In number 12a, we've got theta equals the inverse secant of negative square root of 2. Remember that with your three reciprocal functions, if you have cotangent or secant or cosecant, if you're trying to do this, especially with your calculator, then you want to change it to its reciprocal function. In this one, the reciprocal of secant is cosine. If we're going to change this to inverse cosine, when we do that, we also have to take the inside and flip it over. We would make this 1 over the negative square root of 2. This one, since we're looking for a degree measure, we could do this on the calculator. Be very careful when you're doing this that you know what mode your calculator is in. If we're trying to find the degree measure, we want to make sure our calculator is in degree mode. And then we would just do inverse cosine of negative 1 over the square root of 2. That's going to give us 135 degrees. Remember that the other notation for the inverse trig functions is if you have arc in front of them. This is the same as the inverse sine of negative 0.9217. This is one that we could just do on our calculator. Again, we're looking for a degree measure, so we're going to leave our calculator in degree mode. And on the calculator, this is going to give us a negative angle. It would be negative 67.2 degrees. But this problem didn't ask for the angles to be in any certain interval, so it's fine if it comes out to be negative. In number 13, we're looking for exact values, and this is where we're combining a trig function and an inverse trig function. One way that you can do this is by drawing these as triangles on a graph. What we want to think about anytime we have an inverse trig function, this whole thing is going to be equal to an angle. So we could call this whole angle here theta. If this is true, that means that the tangent of theta would be equal to 2. And since we want to do this as a triangle, we're actually going to write this as 2 over 1. Remember that when we were doing our triangle with the x, the y, and the r, tangent was equal to y over x. So when we draw this, we're going to make our y 2 and our x 1. That would mean that we'd have the point 1, 2 on the graph. And then we're just drawing in our right triangle. So this length is 1, this length is 2, and then we could find our r from there. Remember that r was the square root of x squared plus y squared. That would give us the square root of 5 for the hypotenuse of our triangle. And what we're talking about is that this angle right here is our theta. So now what we're trying to find is the cosine of theta. Cosine is x over r, so that would be 1 over the square root of 5. Let's do the same thing with this one. Remember that arcsine is the same thing as inverse sine. We're going to just make this whole thing equal to an angle. If theta is equal to the inverse sine of 3/5, that means that the sine of theta is equal to 3/5. We're going to draw this on the graph again. This time sine is y over r. Our y would be 3, and our r would be 5. That makes this 5. This would be a 3. And then we would need to figure out the x, the other side of our triangle. That would turn out to be 4. Now what we're looking for is the tangent of theta. Here's our angle theta right here. The tangent of theta would be y over x, which would be 3 over 4. In this one we've got a little something extra to do because we've got 2 in front of our inverse trig function. We're still going to think about this inverse trig function part as being an angle, so we're going to call that theta. What we really have here then is the sine of 2 theta. For this we would want to use one of our double angle identities. The sine of 2 theta is 2 sine theta cosine theta. To calculate this, we need to know both the sine of theta and the cosine of theta. Let's go back to this. Our theta is equal to the inverse cotangent of 12/5. That tells us that the cotangent of theta is 12/5. A cotangent is the reciprocal of tangent, so this would be the same as x over y. That means when we draw our picture, we're going to make our x 12 and our y 5. Our point out here would be the point 12, 5. This side of our triangle is 5, this side is 12. The r would turn out to be 13. For this, we need to know both the sine of theta and the cosine of theta. Here's our theta. Sine of theta is y over r. That would be 5 over 13. Cosine of theta is x over r. That would be 12 over 13. For this, we'd have 2 times sine of theta times cosine of theta. That would be 2 times 5 over 13 times 12 over 13. And that would give us 120 over 169. In number 14, we're trying to find the exact value of s in this interval. This would be the first quadrant, where the tangent of s is equal to the square root of 3. Since we're talking about an exact value, this is where we probably want to look at our unit circle. This is going to be a value for one of our special angles. Remember that tangent is sine over cosine, so this would be the same as sine of s over cosine of s. For this to end up being the square root of 3, some of the values for some of our special angles are the square root of 3 over 2 and 1/2. We would want to make the top of this the square root of 3 over 2 and the bottom 1/2, so that we would end up with the square root of 3 when we simplify. Where this is true, that the sine of s is the square root of 3 over 2, that would be if s were equal to pi over 3. Now, number 15, we're trying to find an exact value again. This time, if we look at our interval between pi over 2 and pi, that is the second quadrant. We want to find the angle where the cosine is negative square root of 2 over 2. That makes sense because cosine is negative in the second quadrant. What we could do with this is first find the reference angle for s, and then figure out the second quadrant angle that would be in the same family. Since this answer is supposed to be in radians, we can do this by families of our special angles. So if we look at where cosine of theta is the positive square root of 2 over 2 in the first quadrant, this would be at 45 degrees, or in radians, that would be pi over 4. So this is our reference angle. Now we want the second quadrant angle that has the same value for cosine. To get that, we're going to take pi minus pi over 4. And that would give us 3 pi over 4. In number 16, we want to find the value of s in the interval from 0 to pi over 2, where cosecant of s is equal to 3.6185. Now this time we're not looking for an exact answer because it tells us to round our answer to 2 decimal places. That means we can use our calculator for this. Since this is one of the reciprocal functions, though, we need to switch this to one of our 3 main functions, sine, cosine, or tangent. Cosecant is the reciprocal of sine, so we're going to switch this to sine. When we do that, we have to do the reciprocal of the value over here. That means sine of s would be 1 over 3.6185. To solve this for s, we're going to use the inverse sign. So that means s would be the inverse sine of 1 over 3.6185. We can put this in the calculator all in one step, and then we're rounding our answer to 2 decimal places. Remember though, since these values are in radians, we want our calculator to be in radian mode. If we have our calculator in radian mode, we're going to get an answer for this of 0.28, rounded to 2 decimal places.